Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to a scientific approach to flood damage assessments webinar. My name is Amanda and I'll be your host for today. In keeping with our custom, Engineers Australia acknowledges the traditional custodians of the countries throughout Australia and recognises their continuing connection to land, waters, skies and community. We recognise Aboriginal and Torres Strait Islander peoples as the oldest continuous cultures on Earth and our first engineers. We pay our respects to them and their cultures and to elders past and present. Before we get started, I'd like to acknowledge that today's event is being hosted with Engineers Australia's industry partner, Silver Wolf Projects. Established in 2007, Silver Wolf Projects is a dynamic, innovative engineering and building consultancy that provides responsive, flexible, expert forensic engineering and building diagnostics for the insurance industry, structural design, permanent and temporary works, and certification services to specialist contractors and builders. I'd also like to acknowledge AiBEC, the Association of Insurance Building and Engineering Consultants. AiBEC has been established since 2024 as the dedicated industry-specific organisation supporting professional engineering and building consultants in the insurance industry. The decision to create this industry organisation is in response to reports by several leading industry bodies that individually express concerns about the significant lack of consistency, professionalism and quality in reporting prepared by engineers and building consultants working with insurance claims. AiBEC aims to raise the professional standing of this sector by providing training and professional development opportunities to its members to enable them to deliver the highest possible level of service to clients and stakeholders. Ultimately, AiBEC represents its members, recognised professionals concerning building and engineering insurance claims. We thank Silver Wolf Projects for their support. Today, we will hear from two speakers followed by our live audience Q&A, and I encourage you to send questions through to our speakers via the YouTube chat box. I'd now like to take this opportunity to introduce our first speaker, Denise Bekier, CEO, Principal Engineer, Building Consultant, Silver Wolf Projects. Denise carries over 25 years professional experience within civil structural engineering, forensic and building diagnostic reporting, construction and demolition contracting fields, and the diverse capacities of director, contractor and employee. Denise has successfully conducted structural design, project management and estimating services within different private and public industries throughout Australia and the Asia Pacific. Dennis has been involved with over 15,000 insurance-based inspections and reports relative to general incidents such as impact, fire and flood, covering notable recent natural disasters, spanning over 15 years within the insurance industry. As CEO of Silver Wolf Projects, Denise has grown the business to over 50 plus wolves nationally with international partners under MOU agreements spanning the Asia Pacific.
Well, thank you very much, Amanda, for that introduction. It's our pleasure to present this webinar on assessing escape of liquid and flood damage relating to builder damage in insurance claims. And this presentation is going to be commencing with myself to introduce the project, and then Associate Professor Gann, who is undertaking the project with his staff and Department of Geotechnical Engineering with the University of Sydney. The project is in association with AiBEC, which is the Association of Insurance Building and Engineering Consultants, and it's a 12-month initiative that we've taken on a board to create a new guide that will assess and give assistance to flood and escape of liquid claims within the insurance industry. So just in starting the presentation, we'll give a bit of a project background on why we're doing this and why this is taken into account, the current methods, what we're looking to as in the objectives and the results, a roadmap, and then the conclusion. And then Professor Gann himself will outline the more technical side of the study and the aims of the empirical guide that we're developing within this project. So within the insurance industry, that is the insurance industry and property, that being residential and commercial properties, is a significant financial service within Australia. Most people in Australia own properties in either residential and commercial and have those insured. In saying that, insurance covers resultant damage from events, and in particular, water-related damage pertains to about $15 to $20 billion annually in damage. And that could be consisting of flooding, inundation, coastal shoreline type erosion, escape of liquid, and that being escape from a fixed pipe or an open pipe such as a water pipe, a flexi pipe, stormwater pipe, sewer, and subsurface moisture damage. So within the insurance industry, there's different perils, but the escape of liquid and flood damage is one of the major losses that we in Australia face. With respect to that, and just putting some figures along that, just to value how much this costs the insurance industry and the construction and design phases, it's about $864 million industry in the sense of damage recorded per year, with respect to an average claim around $19,000, which was recorded in 2024, and around $27,000 in 2025. So it's a significant damage cost to the insurance industry and the insured. And in saying that, the assessment process of that is very important, because in some cases, when it's not clear if resultant damage, that's damage that has resulted from that claimed escape of liquid or flood, has caused damage to that building, that is where dispute and issues arise. So this study is being put together in order to mitigate that, to give clarity and transparency relating to engineering assessment, as well as the building works for all stakeholders within the insurance process. So in saying that, why do we need this study and the development of this guide? And in saying that, why is it time to take out the guesswork out of flood and escape of liquid damage assessment and reporting? It's an interesting question, because at present, the way that engineers, building consultants would look at claims and the way they assess that is through general observation and other forms of documentation. At this present moment, there is no scientific grounds for understanding what the resultant damage would be or has occurred from an escape of liquid or flood. And as the answer says, it would benefit all stakeholders. So this particular study doesn't just side with one, the insurer or the insured. It ascertains a fair and reasonable outcome for all parties. Because what this does, without putting a pun, is draw a line in the sand and saying that what damage could or could not have resolved following an escape of liquid. So in saying that, the reasons for this, it brings science and engineering into the realms of engineering assessment of escape of liquid claims or building movement claims, from that, giving approximate cause rather than just an opinion or an assumed arrangement. This study will produce a zone of influence, and that zone of influence will then start to bring an area of damage that would have resolved from an event, and it will reduce costs in the sense of wasted or lost or incorrect type assessments or building work. It'll bring consistency to reporting, which at present has been identified not to be consistent, is one of the high drawn issues relating to disputes within building and engineering consultancies that work within the insurance industry, in particular with AFCA. And it will bring a better understanding of how claims should be managed, and in turn result in works done or completed when the ground needs to resolve. So what is escape of liquid? What are we looking at in the damage stages? Well, ultimately, an escape of liquid in the sense of a pipe or a fixed fixed vessel or in ground movement is where water escapes from that point. It saturates the soil, and then resultant damage is then claimed or has occurred following reactivity. So at present, we don't have a scientific understanding of where or the zone or the length or the time or the duration or the extent of damage. What we do have is opinions that engineers or building consultants or other professionals provide subsequent to claimed cracking to buildings, rather than some form of empirical formula or method to establish why, how, and when. So, what are we doing at the moment, and what's the difference going to be when this study starts to take into fruition the accounts of the Sydney University and the G-Technical removes that process? So at present, let's look at a general study claim that would be generally received in the insurance industry, and would be, please attend site and provide a report on cause of damage subsequent to a leaking pipe. It's very common in an insurance claim where you'd have a leaking pipe or an escape of liquid from a bathroom from waterproofing membrane, or an overflow or a broken flexi hose in a kitchen that would inundate an area, that would go into the subfloor, subterranean area, cause saturation over some period of time, and then a claim for resultant building movement or cracking or damage would be lodged. And as engineers and building consultants, independent professionals that are engaged by the insurers to provide that advice on causation, at this present moment, we would take this approach, and which unfortunately is not empirical in the sense it's firmed up with science, but more based on reference. So let's have a look at this so you can get a feeling of what we're discussing and what we're intending to do with the study to formulate a better method to finalise a conclusion on resultant damage. So an example would be a very simple one. We'd have a single-storey dwelling, brick veneer, metal roof. Traditionally, maybe an existing structure with post and pier, which has an extension, a concrete slab. Could have been sort of a pre-1950s and then a sort of renovation in the 80s. We've had a description of an event which there's been a leaking pipe within a bathroom wall that has gone into the subfloor and has saturated the ground, and as a result, there's been internal claimed movement within the plasterboard. The leak has been identified through a plumbing test, which has concluded there was a breakage and there was a leak. So we've confirmed that there was an escape of liquid, there was a leaking pipe. The claim now is that that pipe has caused resultant damage, the allegation or the claim of resultant damage, and it's from our assessment as engineers at this stage, without the study that we're discussing, the methods of how we would use to determine whether that was or was not a result of the event. So in essence, we've got a floor plan here where you've got an approximate location of where the leak was, which is outside of the bathroom. And then we have areas of claimed damage would relate to bedrooms 1, 2, and 4. And they've been identified by those red squares. And some photographics here. Well, you've got a single-storey dwelling, as we've said. The damage that has been rectified. So that's where the rectification of the pipe was identified and now fixed outside of the bathroom. That's external. And then sort of consistent damage that's been claimed as a result of building movement. So this would be within the area of the posts and piers. So differential movement would be consistent with the claim of reactivity from the ground. And in saying that, other types of cracking and movement within the plasterboard, that again has been claimed as a result of the escape of liquid and resulting building movement from ground reactivity due to the pipe leak. So it's very common. This would be a very common assessment for most engineers or building consultants looking at causation within the insurance industry or other building diagnostic professionals relating to claimed ground movement, and in this case from reactivity. So at this moment, we would generally use standardized methods of adopting diagnostics. That would be, in essence, looking at the building code, the Australian Standard 2870, and the CSIRO publication on foundation maintenance and footing performance. And at this stage, most engineers and building consultants would look at that, identify the ground conditions, look at the type of damage, and make an opinion or provide an opinion on the basis of their experience and relative to the length of crack, size of crack, maybe the freshness of it, the thickness, and the way that it has cracked, the geometry of that, to assess whether that was as a result of any ground movement. The problem lies with this is that it all is all based on visual evidence. It's all based on assumption and correlates with the experts or the engineer or building consultant's experience. It doesn't have any scientific basis in the sense of categorically nailing down that this was a clear result from the leaking pipe. Yes, it could be building movement as a result of ground movement, or it also could be building movement due to articulation or poor workmanship. So we start to remove ourselves on a balance of probabilities on what the causation would be, but again, we're not identifying exactly that it's a result from science or geotechnical study that this was due to ground movement from a leaking pipe. Other methods, obviously, is the use of the plumbing test to identify whether there was a leaking pipe, which is standard. We actually have to identify whether there was or wasn't, but this again doesn't determine whether the resultant damage is claimed is a result of that leaking pipe. And we also do use historical data such as water rates to see whether there was a spike in water. If it was a live set of water taps, we could then establish whether there was an increase in water loss. But again, that doesn't show you or prove to you that the resultant damage as claimed was due to that leaking pipe. One of the big tools in diagnostics, and in particular with building and earth moving and ground movement, and it's been introduced specifically within the insurance industry, is floor level surveys. And floor level surveys are a method of measuring the floor level over the entire floor plate to establish whether there's any movement, the geometry, and any distortion. The issue with that is that it's relative to the time that you take that measurements. It doesn't have a datum of what was previously there, nor what was there afterwards. It's set in the time of taken. So it's not really a clear method of diagnosing whether the damage had occurred. It just shows you a real lifetime of what the floor geometry is. So what's missing is a datum point, the datum point of what was previously there, or in the case, what we're looking at, a zone of influence to establish, well, if the leaking pipe occurred in the bathroom and we established through this guide or through the scientific of ground movement, through time and reactivity of soil, that if a pipe leaked for 7 days and the ground was highly reactive, then subsequent to that permeability and the reactivity, then an expected zone of influence from the bathroom would be 3 meters. So if we were to establish that, then we could then have a datum, because you would do the measurements within the 3 meter radius and outside of the 3 meter radius, and then you'd establish if there was a point of difference in height, then there's differential movement, therefore it was a result. So it gives you another piece of evidence, substantiated evidence, that can enable you to format whether this movement, as claimed, was a result of the leaking pipe. So in conclusion, we would generally identify, that damage may have resulted from soil reactivity, building movement, thermal expansion, contraction, poor workmanship, and defect. But in saying that, we haven't got, at this very moment, a categoric method of determining a correlation between damage, leaking pipe, and building movement. And in establishing this guide, that is our aims and objectives, because at this moment, we don't have really a validity in the sense of another form of approach or evidence that engineers can use to correlate their visual inspection, their reference against standards and codes, and the leak itself. But if by creating the guide and that being a zone of influence around a point of damage, then this then can be a line in the sand where differential geometry can be used to prove that it was or wasn't a part of that leaking pipe, as well as the methodologies of how that would have occurred if it didn't correlate with the study itself. So it's very important that this piece of information gets produced, because it now strengthens both argument, approval, or rebuttal on a leaking pipe claim for both the insured and the insurer. In saying that, a lot of disputes occur as a result of this. The Australian Financial Complaints Authority, that being AFCA, is within the Insurance Code of Practice the point of arbitration where external dispute resolution within insurance claims are met between the insured and insurer, and they produce the final reading on that, subsequent to advising and reviewing the advice. And in the approach to the proximate cause publication in April 2022, they really do put forward the factors that they would be requiring in order to make their determinations. And this would add more credence and value to that by providing more evidence in the sense of what they would determine resultant damage or approximate cause rather than just an opinion and visual. So this again is an assisting matter and an assisting piece of information that enables better claims outcomes, clearer resolution and transparency with the insurance process and claims handling methodologies with insurance claims. So what we're trying to do here, in essence, at the moment, we've got one equation and two unknowns. What we're intending to do is bring one equation with one unknown and then create that. So at the moment, we've got an escape of liquid, but we don't know the duration, or we can establish the duration. We know the soil response, but we don't know the extent of damage. So what we can do with that equation is, if we know what the soil is, if we know what the leak is, then through this guide, we can work out an extent, and that will give us a formulated response to resultant damage. So this now creates an ability for an engineer or building consultant to now finalize in more clarity what resultant damage would be, rather than just speculative or assumptions on the damage methodology or geometry or visual assessment. So it becomes a bit of a mathematical equation, and this mathematical equation works then with other tools such as floor level survey. So if we've got an established zone of influence, we can use the floor level survey to determine whether differential movement between the zone and outside the zone has occurred. That then creates an equation or another form of evidence to suggest or indicate that the balance of probabilities that escape of liquid has caused damage. So that is very important as well. So what we're doing is we're bringing in the science in the engineering and removing the assumptions to bring a solvable property equation with respect to saturated ground as a result of escape of liquid. So the zone of influence then starts to determine the unknown. It creates now the variable that we can use to determine whether damage specifically from an escape of liquid point at a period of time relative to a type of ground, how much would that have radiated and where would that have propagated as a direct result of the escape of liquid. So this now starts to become more clearer on the resultant damage, which is where, as insurance, building and engineering consultants, we've been asked to provide that causation report so the insurers can make their determination whether it was a result of the claimed event. So what we're trying to do here, and in leading up to Professor Gann and his presentation with the methodologies of how he's going to create this guide with his team, the Geotechnical Department of Sydney University, the aim of this study and the guide for industry is that it starts to move from opinion-based assessment to research-based assessments. What we're trying to do here and the objectives of the guide and the zone of influence is that we're moving away just from assessing damage from a visual inspection of diagnostics of building movement and claims of damage, now to more science and geotechnical based assessment relative to the time of leak, the extent of leak, the reactivity of the soil, and then in essence the radial movement that would be propagated subject to the study and the science and engineering behind it. So I now am very proud to establish the understanding, the objectives of this study, which AiBEC has been involved in with the University of Sydney Engineers Australia, and I'm pleased to now present Associate Professor Gann for him to advise on exactly the science and the engineering behind the study and what it's going to take to bring this to fruition.
I'd now like to welcome our second speaker, Associate Professor Gann, and Acting Head of School of Engineering, the University of Sydney. Associate Professor Gann holds a PhD from Karlsruhe Institute of Technology, Germany, and is a Fellow of Engineers Australia. Associate Professor Gann's research expertise spans geomechanics, granular materials, and fluid transport in porous media, making him a leading authority on complex soil-water interactions. His work consistently blends fundamental engineering science with practical industry applications to solve complex infrastructure challenges. He is currently collaborating with Silver Wolf projects at AiBEC to develop formalised, empirically rooted approaches towards reliably assessing building movement and property damage caused by floods and escaping liquids. Please welcome Associate Professor Gann.
Good afternoon, everyone. First of all, thanks Amanda for the introduction, and also thanks Dennis for setting up the background of our project. So from now on, what we were trying to do is just giving you some updates of this project that we have just started 3 or 4 months ago, and just giving you some also the plan of what we were trying to achieve in the duration of the project, working with Silver Projects and AiBEC together. As Denise has already providing a very good overview of the project background, so I will dive immediately into the problem we are facing. So I will record this slide, which probably already shown early in the Denise's talk, just showing the key aspects. What we're trying to looking at are these 2 zones of influences regarding the escape of liquid. Now we identified 2 key zones of influence in this context. The first one is the zone of influence in terms of water content. This is how far the liquid transport after the happening of the escape of liquid. The transport of fluids will alter eventually the effective stress state, leading to further settlement or heaving in different contexts. Then the second zone of influence is actually looking at the settlement due to the escape of liquid events, which leading to the floor leveling, as we shown already seen in the early case study that's showing the leveling of a building. Now, what we are trying to do using this is not only looking at a given value, but also looking at the temporal and spatial variation of these 2 zones of influence due to the moisture change. And our topsoil layer, where this liquid leakage will be influences, are typically in the unsaturated situation, where the soils basically having partially water, partially air in its void space. Now, if we were looking at a pile of dry sand, and if we try to drop in them from the space, we can form basically a typical stable structure of the dry sand we call angle of repose. So for our geotechnical engineering, this is the basic idea of how the soil's strength will look like. And for this type of sand, when we trying to starting to add a little bit of water, not too much, or we keep adding water up to a certain point, we're forming eventually all these very interesting structure, including at a certain range of water content, to forming a tower of sand. Basically, the sand can support itself with the presence of combination of air and water in its space. Now, if you keep adding water and oversaturate that water tower in the middle, and until the point where the sand go to the fully saturated state, which is submerged in water. So the pile on the rightmost of the screen is similar to the complete dry sand pile on the left-hand side. Now, basically what this example shows, even though this is purely talk about sand, is just to want to show that how the water content was changing over the variation of the water content to eventually the strength of the sand as a sand pile to forming this structure. And we can characterize by using one simple variable called degree of saturation. Basically, that's the ratio of the volume of the water to the volume of the void. Now, in soil mechanics, what we're trying to looking at these unsaturated soil levels is basically characterize three volumes of the solid and the void, which combines the volume of water and air in the void space. Now, in the leftmost figure, that shows basically how we can define basically void ratio, degree of saturation at different state. However, in more reality scenario in the middle, where we can identify if it's underneath the footing, we're finding an area where the soil is fully saturated. So we can define this as a water table, and below which all these soil will be fully saturated, above which we're having a zone where air and water are coexistent in the void space, forming an unsaturated zone, where these zones were eventually being influenced by our escape of liquid events. And the rightmost case is showing a study, if you're looking even into details, how these water were distributed in that void space. Just in a very simple example, much simpler than sand, is the glass beads systems. You can see the water were forming in different geometry, and these interfaces between the air and water providing the strength, additional strength to the soil samples. Now, if we're starting from the simple example of sand, and however, in the escape of liquid cases, typically we are looking at foundation soil type rather than silty clay or clay. Now, this slide just shows us for different types of soil types, and what is the soil water characteristic curves representing on the left on the suction happening in the soil, and on the right the hydraulic conductivity of the soil at different degree of saturation. So here, say the effective saturation. Now, all these curves are plotted in a vertical space in the logarithmic scale. So if I'm comparing my clay sample and sealed sample, they differ in a few magnitudes, not in terms of matrix suction, which is providing the pressure, additional pressure in the pore space, as well as the hydraulic conductivity, which allows the free water to move in the pore space. Now, this graph is also showing basically the range or the possible range of different types of soils, because to our AS standard of the soil type, we're having multiple types of soil, and we can see the range of the property will be changing quite dramatically in that space. Now, this leads to us to looking at how the soil type eventually will impact our escape of liquid as a key input parameter here. Now, if you look at this graph, we can also see a dotted line and a solid line, which showing basically the range of the drying and drainage and wetting pathways of these soils at different water content. And this slide is just showing, say, if we are looking at more details, how water was distributed in the space in the drainage and wetting paths, the distribution of water will be quite different. This is leading to a study of looking at not only the escape of liquid, but also how the restoration or recovery stage, the water will be contribute quite differently in the pore space of the soil. Now, we won't look in details in the granular scales how the water will distribute in the pore space, but rather we are facing a challenge that we can't model this system between the interaction between the soil and water in the pore space. Now, what we adopt in this project initially is we need to adopt some kind of quantitative behavior to describing what is the effective stress descriptions in the unsaturated soils. So we're here basically using the Bishop's equation, distinguishing basically the total stress, effective stress, and pore water pressure. And these pore water pressure and hydroconductivity can be described by the soil characteristic curve we just showed in 2 slides before. Then the elastoplasticity of the soil under the deformation at the different water saturation can be using the effective stress, describing the modified Kankle model, describing the yielding, hardening, and flow rules, plastic flow rules of this model. Now, finally, the moisture transfer can be captured by the recharge equation, and using the relative hydraulic conductivity describing as a function of the degree of saturation. And eventually, when the saturation is reaching to 1, or it means the water fully occupied pore space, the hydraulic conductivity will be go back to the permeability at the fully saturated state, K sat, as indicated as the last paragraph. Using the constitutive law model we just discussed in the last slides. So in our projects, what we're aiming to do is developing, first of all, a physics-based numerical model that is being implemented in a finite element solver. And we do have multiple finite element solvers. And here in this project, we are starting with a MATLAB interface with a console finite element package to study the building scale studies. Then we study, generate at the same building scale models in different parameter space. We'll discuss a bit later on this parameter space of the soil loading and water leakage conditions, and generate a large data set that used to be training for a validated surrogate model, which in the very beginning we had validated this, our finite element analysis result versus some available long-term field data. Then using that large data set by varying different parameters and consider uncertainty and the probability of these parameters to be eventually develop a data model used later on in the field. Now, to be more specific looking at this is, as in this project, we will have 3 phases. The first phase is using the implement numerical model at the building scale on left shown on the slides. And then we're using different range of inputs parameters, which contains soil property and water tables and site conditions and escape liquid conditions, including how much water in terms of volume, but also the duration of the leakage events. And by varying all these variables, we putting in our model to generate large data set, then using a data-driven model to replace eventually the finite element method to having the inputs to giving you the outputs, which of concerns by illustrating 2 zones of influence. First, about liquid transfer, how far the liquid goes to, and second, the soil deformation, how far the settlement influence goes to. Now, to give you an example is we're starting with a building scale model, which could be specific. So for this process, we are looking at a specific condition, showing a finite element model on the right. We're using an axis symmetric case, and in the center, we're having a loading zone, in this case of a radius of 2 meters. And underneath the footing, we're having the escape of liquid site, having a liquid inlet of here as a 1 meter, as an example. Then in this specific case, we adding basically the water table below 5 meters and looking at this model using a given set of soil property, site conditions, and escape of liquid loading listed as inputs parameters, which contains the 4 in here show 4 parameters as example for the soil model, and 4 parameters for the site conditions, including the pre-consolidation pressure, water table depths, loading of the foundation, and the size of the foundation loading. Then in the escape liquid loading, we have 3 parameters, basically the water flux phi going through the leakage site, how big is the leakage site, R, and the duration of the leakage event, T. Now, eventually, the finite element model in this specific case will give us a zone of influence and a settlement profile over the time. Now, before we do the hydraulic test, what we do is do a preliminary loading on the foundation on the soil body, which we mentioned of the setting before with the water table on this depth. Then we can see the settlement will be changing over the loading we applied for different pre-consolidated pressure. Then what we're trying to in here is finding a pressure critical to the foundation, then apply that constant pressure. Then we start our hydraulic loading. Now, in this animation, what we can see is from the leakage side, so how the water will transport from the top going down to reaching the water table over a long duration of time, and the profile is still evolving over time. On the right, basically showing your contours of the change of water content over time at months, a quarter, and a year in this case. So all these are study conducted basically in this final analysis. So looking at the time evolution of the liquid, showing how far this liquid influence zone is developing over time. Now with the water distribution, so basically the water will infiltrating into the unsaturated zone on top of the water table, that is changing the stress conditions while we are given a constant loading on the top. Now what will happen is by adding the water, so it's changing the suction state, and with the water is reducing basically the soil's effective stress and reducing the strength. We will tracking basically the volumetric strain evolution over time again underneath the footing. On the right is plotting again months, a quarter, and a year, how much this the additional settlement influence zone is evolving over the time. But we can also track in basically the settlement profile during the excavate of liquid events, looking at for a given position over the duration of time, or the total profile of the surface over the time on the right-hand side. Now, all this study at the moment, so we're putting basically a different saturated hydraulic conductivity in a range just to see what's the influence of this inputting parameter will be changing basically the settlement over time. Now, this is one example of very case specific. What eventually we want to do is to formulate this as a key part of our project roadmap for the months to come. Now, what we have done here is basically we looking at a setup of how we transfer the inputs, putting in a hydromechanical model, and providing the outputs in terms of settlement profile and zones of influence. But eventually, what we're trying to do is to varying our input parameter, basically going through a wide range of soil properties, site conditions, and escape of liquid loadings, shows the parameter in the bracket just below the box. Now, as we know in our standard, there is a multiple category of soils. So the study is basically will be using a lot of soil properties, putting a model to generate the perceived or predicted the settlement profile. Now, with this information, what we're trying to do as next step is to using that data set to develop a data-driven or surrogate model, just replacing the calculation for case-specific or soil type-specific cases to using that to having a very rapid data integration assessment tools. Now, a typical example is shown on the right bottom side. So if we do have a map, and we were having some kind of soil characterization information, and with the building conditions to fill the parameter space, then if we say this event happen of excrete liquid, say given a volume of a liquid escaped and given the duration of that escape events, so we can have a prediction over the time what is the influencing zone in terms of water content change and additional settlement. So that's basically the total plan we were having. So up to now, since we only have 4 months completed for this project, so what we achieve right now is we identify the key influencing factors of the escape of liquid event related to the assessment to identify. Then we build our finite element access model, which is case specific, showing a few showcases of predicting zones of influence in terms of water transfer, as well as the soil deformation, just to show how the finite element can do for this relevant problem. Then we also discuss of the roadmap, how we can achieve a rapid engineering assessment tools. Just need to be going through a validation stage, need to go through the data training stage in the next phase of our project. Of course, there's a few open questions. So we find a few validated long-term site monitoring data, but the more data, the better for the prediction. So this is also open for the community, that if we having some kind of long-term monitoring in terms of moisture change, in terms of settlement, in the event of escape of liquids, that would be much welcome for us to do additional validations. Now, we also know that the range of the model parameters or the conditions are quite large. So we know that we need to consider about the probabilistic analysis to consider all the uncertainty coming from the soil type, coming from site conditions, and providing some kind of guidelines to show what's the upper bound and lower bound of the settlement or liquid transfer in terms of zones of influences. Now, we also shows most of the case studies, and also in the near future, most of the cases are looking at the wetting paths, which the water is enter into the foundation and changing the water distribution as well as the foundational settlement. So what we know for sure is restoration and recovery phase, where we're having a drainage set when the drying of the soil is happening. This will be additional settlement and things which I think is quite relevant to the flood assessment, the post-flood assessment, will become very critical, and our model actually can somehow by extending to do this domain. Now, on the right-hand side bottom, and I recall what the case study Dennis has just explained to you early, is if you have a floor plan and you know the site of liquid escape. So our model in the building scale is it already can show you over the time or over the volume how this zone of influence is developing over the whole duration. So this is give us already some idea to get connecting the missing parts in that equation for the assessment. And finally, I would like to thank our teams. It's very fantastic working with our industry partner, and as well as our group, research group at the University of Sydney. So including Professor David Airy and our PhD student Hai Yizhong. We'll welcome for any questions if you have.